Welcome to Soil Structure Engineering Problems. Will be the lesson 8 of this YouTube channel, and we are going to talk about a very interesting topic, but only basic concepts of the theory of plasticity, because it's just a very introductory lessons about plasticity and making comparison with some with another model that you know better, that is the linear elastic model. So in this lesson we are going to try to understand the difference between elasticity and plasticity. We are going to try to understand the difference between an isotropic linear elastic model and an isotropic bilinear elastic model. We are going to use the computational geomechanics approach using Ansys Workbench mechanical to run a numerical simulation in 3 dimensions to see the difference between these two worlds on these two models, the linear elastic and the bilinear elastic, which is a plastic model. So why we need to study plastic models and why we need to set in a software or to develop a model with plasticity? Because in reality, the theory of elasticity that we use a lot have limitations. So we need to be able to simulate numerically more complex material than the elastic ones. So we need to characterize the ultimate and failure states, because we are, as engineers, in charge of the study of the failure processes to avoid the failure in our structures. And we want as well to be able to face permanent deformation that are common in civil engineering structures. And we need to model the changes in behavior, because our materials, for example, the steel, the reinforced concrete, maybe start behaving as linear elastic at the beginning, but sooner or later, when we increase the value of the loads, we are going to change this behavior from linear elastic to plastic behaviors, for example. That is the topic of this lesson. On the screen you see the typical relationship in matrix forms that show the relation between the stresses, this vector you have in here, and the strains, this other vector you have to the right, through this matrix in the middle that is the stiffness matrix for the relation between the stresses and strains. When you have a linear elastic isotropic material model, this relation is very simple to be established, because it's just a multiplication of a matrix by a vector. For example, here we find the stresses multiplying this matrix by this vector of strains. When we say that the model is isotropic, this means that the behavior, the mechanical behavior of this material, this mathematical material that is defined mathematically, is the same in every single direction of the three-dimensional space. This produces a reduction in the number of elastic parameters we need to define the module mathematically. And when the model is isotropic, the only 2 elastic parameters we need to define this model are the Young modulus E and the Poisson ratio nu. So as you see, sorry for that, this is a test of my fire alarm. So in this case, with just these 2 parameters, the Young modulus and the Poisson ratio, we have defined the relationship between the stresses and strains of these materials defined mathematically. But when we have plasticity, this is not enough, as we are going to see in a moment. On the screen now you have a typical stress test, an axial test on a cylindrical bar. And we see that if the material is brittle, the material will behave like the line I'm indicating right now in violet. So you will have an initial linear elastic behavior, and suddenly you will have a change in the behavior, transforming the behavior or turning the behavior from linear to non-linear, and immediately after you will have the failure of this material, because this material is fragile. or brittle. If you have a ductile material, the ductile material presents a more complex behavior. So in the first instance, you will have a relationship which is linear, as you can see clearly because this is a straight line. And in this portion, until you reach the value y, you have what we know as a linear elastic isotropic model, for example. So this line, this straight line from O to this point y in here, will respond to a mathematical behavior as the one I have shown before. So we just need to define the Young modulus and the Poisson ratio. In this unidimensional experiment, you see that there is only the Young modulus as a parameter shown in the figure. There is no Poisson ratio in here. And this is because the Poisson ratio plays a role once you go to a two-dimensional space or a three-dimensional space. Because remember that the Poisson ratio is the relationship between the strains in two perpendicular directions. But after you increase enough the loads on your material, on your sample, for example, in the lab, you will notice that there is a sudden change in the behavior. So in this portion I'm showing now, there is no a linear elastic isotropic behavior anymore. So actually, if you consider that the Young modulus as it is the slope of this line, during the linear elastic isotropic regime, the value of the Young modulus is constant. But once we reach this value and we change the behavior, because this value is the slope, so the tangent of this line, the value for the Young modulus, if you want to call it Young modulus, is not the Young modulus anymore. The values of this parameter is not constant anymore and will change along this curve that is describing the deformations or the strains in relation with the stresses when you are doing a test on this bar. When you discharge the loads on your sample and you have reached this level of stresses, the discharge will be more or less parallel to the initial straight line you have in the elastic regime. And when you recharge, you will follow again more or less a parallel line to the initial line of the linear elastic regime. And now your material will have recovered this linear elasticity behavior, linear elastic behavior, but until it reaches again a point where there is a sudden change and the material becomes plastic again. As you see, if you do successive cycles, you will experience the same behavior as I have explained before. And every time you discharge and reload, you will see that this parameter y will increase, and this is the yield strength, so it's a limit where the linear elastic behavior turns to a plastic behavior. So this means that in the process of unloading and reloading, we are changing the parameters, one of the properties of these materials, and this material is becoming stronger in some way because the yield limit is increasing. So then, when we have plastic behavior, we will need a more sophisticated mathematical model to catch and to reproduce this behavior for ductile materials, ductile steel, for example. And this is the reason why we need to set and we need to study and we need to understand plastic models. So all of this can be reproduced, because this is an actual behavior of a material in the lab, can be reproduced mathematically using simplified models that are called bilinear models. For example, on the screen now you can see a typically what we call an elastoplastic model, and in this particular case this is an elastic model because you have the straight line in here with certain slope that is the Young modulus, and the plastic regime is a perfectly plastic regime because this straight line, the second line of the bilinear model, is an horizontal line. And in this case, when we discharge or when we unload and we reload the material, we just have a line for unloading and reloading parallel to the first line of the elastic regime, and we don't produce any change in the yield limits because the second line of this bilinear model is horizontal and is representing a perfectly plastic model, where once you reach this value of the yield limit, you don't have any resistance and you just have plastic deformation with constant loads. Of course, this simple model is not enough in many cases, and there are others, and we are going to focus in this explanation in the bilinear model with hardening, because it's a very useful model in engineering, in civil engineering, and because show that it's possible to have a simplistic model that reproduces a ductile material behavior as we saw before. So in this case, for example, we have a linear elastic regime at the beginning, and after we have a sudden change, we have a second line that represents the plastic regime, and when we unload and reload, we are going to be able to capture the improvement or the increment in the yield strength of this material. So we are being able now to reproduce more or less what happened in reality. Remember that what happened in reality is the test, and now we are going to have a bilinear model that will capture this first elastic regime and will capture this second plastic regime just with a line. This is a simplification, and we are going to be able to capture what happened when we unload and reload by changing the value of the yield strength in our model. So for this model, this bilinear model with hardening, we are going to be able as well to capture the plastic deformations that are permanent. We are going to be able to capture the elastic deformation that they are recoverable. So we are going to have a model that is much more interesting than the linear elastic one, because the linear elastic one is a very limited model that only allowed to reproduce the first part of a real behavior of a material, for example, a ductile steel, that is represented by the first line from the origin of these coordinates in this space of stresses and strains. So now we have a little bit more understanding of what is what are these concepts in the one-dimensional space. We can study the three-dimensional space by using a software. So I'm going to open the model I have created in Ansys Workbench now. So what I have done is I have created a very simple geometry that simulates the test in one dimension in the lab on a bar. And I have set a linear elastic isotropic model in here. And I have set as well a bilinear model, an isotropic bilinear model. So in the first place, I will add in here that this is an isotropic linear elastic behavior. And this one here is an isotropic bilinear behavior. And it's elastic as well. No, it's not elastic because this is plastic. So I will add in here plastic, or even better, this will be elastoplastic, because we'll include both the elastic regime and the plastic regime. So let me show you first what I have done in terms of the geometry. So I have created a geometry that will allow us to study this behavior in three dimensions. So I have created a bar. This bar is 20 millimeters in diameter, and I have decided to divide the bar that have a length in total of 0.5 meter in 3 different sections to focus the attention in the middle where the interesting thing happens. And because I wanted to avoid having the influence of the restrictions I will apply to these extremes in terms of loads and displacements, and to avoid the influence of these restrictions on the middle of the bar where I want to focus my analysis. So it's a very simple geometry. So I have just extrude the first section as you see on the screen, and after I have extrude the second section, which is 100 millimeters, and the final section is 200 millimeters. So 200 plus 100 plus 200 is 500 millimeters, which is half a meter, the length of this bar, and 20 millimeters is the diameter, if I remember well. Yes, the diameter is 20 millimeters. So this is the geometry. Let's go to the isotropic linear elastic model. So once you export to a structural analysis in Ansys Workbench mechanical this geometry, you have to set a few things. So for example, in terms of geometry, you have in here the top steel bar, the central steel bar that will be the one we are going to use for the results, and the bottom steel bar. So I have as material just an isotropic linear elastic steel that I have set with these parameters. So the Young modulus is 200 gigapascals, the Poisson ratio is 0.3. The software have calculated the bulk modulus and shear modulus based on the Young modulus and the Poisson ratio. And I have set these values for the compressive ultimate strength and the compressive yield strength and the tensile ultimate and yield strength, as you can see on the screen, just to have the possibility of calculating some sort of safety factor. So in terms of connections, of course, I will have two connections between the three bars, cylindrical bars I have created. So I have established that these connections are bonded because I just want to see what's happening in the middle in this portion of 100 millimeters of length. This is the mesh of the model. It's a fine mesh to have accuracy enough for the analysis. And in terms of loading, because now we are going to have a model which is not this one because this is linear elastic, but the plastic model will be able to capture the change in behavior. I will test these models using 6 different steps of loads, where I will increase the load in this case from 0 to 100,000 newtons, and I will unload to 0, and I will reload again, and will unload, and will reload again, and will unload. So I have 6 different steps to apply the force because I want to see how this model behave in loading but in unloading as well. I have fixed one extreme of this bar, and I have applied the force on top of the bar to simulate what happened in the lab. And after running, this is a very simple model because it's linear elastic, as you see in the material. It's isotropic, it's linear, and it's elastic, so there is no any complications in terms of plasticity. So it's run very well without any issues. And when you check the deformations, for example, directional in the Z direction of this portion in the middle that we have selected, you see what happened in terms of minimum, maximum, and average deformation. So I will show just the maximum because it's simpler to see. So during this process of loading and unloading 3 times, you see that the deformation is just elastic because this model is linear elastic and isotropic. So you reach a maximum of deformation, and when you discharge, you recover all the deformation because all these deformations are elastic just because the model is elastic. So if you just make a video, you will see that this material will deform in the direction of the loads applied and will recover all the deformations once you unload. So I'm trying to change the scales in here to appreciate in a better way what's happened. So this model is nice, but it's very limited because independently of the values of the load I apply in here, when I load and unload, I will recover all the deformation, so I won't be able to reproduce any plasticity in here. So you can see the distribution of the, for example, equivalent von Mises stresses in here. You can locate the maximum, in this case, more or less in the middle of the sample. And you see that the maximum value for this stress is 318 megapascals. So if we remember what we have defined in terms of yield tensile strength, which is 250, evidently in this case we are over this limit. So in theory, this material should be plastifying already, but because my model is linear elastic, it's not able to capture this change in behavior even when we are over the limit in terms of yield strengths. The maximal stresses are these. So be careful when you check the values of the stresses, because the values of the stresses will depend in which step of load you are. So for example, in here you see a maximum because you are in a peak where we apply a load, but if we position the results in this point in here where I have unloaded completely the bar, and you recalculate the stresses, of course the stresses will be zero because we are recovering all these deformations and the stresses you have reached in the maximum value for the load. When you unload, you are recovering and you go back to zero stresses. The same thing will happen with the maximum principal stresses, and the shear stresses, of course, will behave in a similar way because this model again is just isotropic and linear elastic. When you check, for example, the one of the safety factors that this software is able to calculate, and you position, you analyze what's happened at the different stages when you are applying the loads, you see that in this case, for example, at this step, where we have a peak in terms of loads, because we have a maximum load applied at 1, 3, and 5, you have certain troubles in terms of the safety factor, and this is logical because, as we have checked before, the all Mises stresses have reached, for example, a maximum that is beyond the yield strength. So it makes sense that the safety factor is showing that at this level we are going to have some problems with the safety factor, because we actually are failing in our real material, but this model, because its limitation, is not able to change the behavior of the material properly following the plastic behavior of the real material. So it's a valid model, it's a linear elastic model, what we use a lot in civil engineering, but certainly have certain limitations. Let's see now what's happened if you set a bilinear model, which is a simple model to capture, let's say, plastic behavior. So I'm going to go to the engineering data for the bilinear model to show you in details what is the difference. So in there, I have set again the same isotropic linear elastic steel, but I have added as well an isotropic bilinear elastoplastic steel, where I have defined the same elastic parameters as before, but in addition I have bilinear isotropic hardening that you can find in here in plasticity, so it's the first option. And when you define a bilinear isotropic hardening model, what you do is you need to add again the yield strength that for consistency I have chosen to use the same one as in the elastic model, and you need to define as well a tangent modulus. A tangent modulus is the module of plasticity, is the module that defines the slope of the second line in your bilinear model. So this bilinear model, remember, is isotropic, so the behavior of this plasticity will be the same in every direction of the two-dimensional space, and it's going to be constant in the sense that the plastic modulus will be constant, so it's not going to be a plastic module that will change with loads or stresses. So it's a very simplistic plastic model, but it's much more powerful than the linear elastic isotropic model that we have studied before. So notice that the plastic model is very small, it's just 1000 megapascals, when the Young modulus in the linear regime is 200,000 megapascals. So this is almost an elasto-perfect plastic model, because this is very, very close to the horizontal line we saw in the theory before. But anyway, presents certain hardening, because there is a slope, there is a value for this tangent modulus, so it's gonna be able to capture the change in the yield strength when we load and unload our bar. So I'm going to go now to the model in the structural analysis framework. So this is it. So this is my isotropic bilinear elastoplastic behavior model. So in this case, I have the same geometry as the linear elastic model. The materials are of course different. This was checked already. The connections are the same, because I want to have a good comparison. The mesh is the same as well, and the analysis is made as well in 6 different steps. But in order to make things more interesting, I have set these loads with different values just to see the capacities or the possibilities of this model. So I have set the first step. Let me just check the values in here. So the first cycle is I increase the load to 20,000 newtons, from 0 to 20,000 newton. After I reduce it to 0, after I have increases to 50,000 newtons, after I have unloaded to 0, and after finally I have load the bar to 100,000 newtons, and I have unloaded to 0 again to see what happened. So in terms of directional deformations, as you see now, and we are going to see just the maximum to simplify. What you see, what happened now is, and let me just zoom in this. So when you do the first cycle, so you reach a certain value of deformation, and when you unload, you recover all the deformations, because in the first step, with these 20,000 newtons applied, and if you check the, for example, the von Mises stresses, what you see is that the maximum von Mises stresses are under the yield strength that is equal to 250 megapascals. So in this case, you are not plastifying the model yet, the material yet, because you are just adding a load that is in the elastic regime. So in terms of deformation, what you see is the deformations reach this maximum of 0.09 millimeters, or almost 0.1, and you recover all the deformations. In the second cycle, again, because we can check that if we go to the peak of the load in the second cycle, and we show the equivalent stresses here. So I will recalculate this. So in the second cycle, for 50,000 newtons, you see that you still, in terms of equivalent stresses, not reaching the 250 megapascals that is the yield strength of this steel. So evidently you are not plastifying, so the model is still remain being elastic, so isotropic and linear elastic. So when you unload, you will recover and you will go back to 0 megapascals in terms of the equivalent stresses, and you will recover all the deformations as well, because this model, even when it's bilinear, is still being in elastic regime, because we didn't put any load that produce enough stresses to plastify the material. In the final cycle, if you go to the force in the final cycle, where you reach 100,000 newtons in terms of load, what happened is that if we check, for example, the equivalent stresses at that level, let me just recalculate and let me show just the maximum, you see that in terms of the maximum equivalent stresses, you are at 331 megapascal now, so over 250. So we are reaching at some point the yield limits, and we are over the yield limits. So if you see what happened in terms of the equivalent stress when you unload after that, you see that the equivalent stresses are not becoming zero again because you have plastified. We are beyond the plastic limits. If we see the deformation, you see that at the final cycle you are not recovering all the deformation, so you are having plastic deformations already in here. So you are just recovering the elastic part of the deformation, and in here you capture, in terms of deformation, the change in behavior, because this has changed the direction now. So this is the moment where we start the plastification of the material. So at this level of deformation, we have reached the yield limit and we change suddenly the behavior. In terms of all the other stresses, you will notice the same thing. So if you construct this very simple model, you can see in every single detail what's happened. And if you check safety factors, for example, you can notice that the safety factor behave in a different way now. So there is no a linear behavior anymore because the model is not linear elastic anymore. And again, you need to be careful when you check the safety factor, because the safety factor will depend on the loads, of course. And you see that for the first load, for example, let's say for the force of 20,000 newtons, the safety factor is not too bad because the minimum safety factor you are having in here is about 4. So you can feel yourself safe with this safety factor. But if you go to the second load, where you reach 50,000 newtons, in that case the safety factor will be less generous, let's say. So we still over 1, but the maximum safety factor at some points of your sample is reaching a value about 1.5 or something like this. And if you go to the maximum loads applied to this case, which is 100,000 newtons, you will see that the safety factor is becoming dangerously close to 1 in many points, and actually in the majority of the points you are under 1, as you can see in these results here. So for 100,000 newtons you are definitely in bad conditions. So as you see, even when the bilinear model is a very simple model, it's a model that is able to capture important things in terms of behavior. So now we are able to study materials like the one we started explaining before. So you are able to reproduce the behavior in the linear elastic regime. You are able to capture the change in behavior when you read the yield strength. You are able to reproduce behavior when you unload and reload your material, your sample. So this is a much more powerful model than the isotropic linear elastic model that we use commonly in civil engineering. It's simple, it's very effective. It's still a model that is isotropic, so we are not capturing different behavior in different directions. This could be a limitation, for example, when you run models in soils, because we know that the soils are not isotropic, but is as a first model to use plasticity is a very good model because it's simple to understand and it's very powerful indeed in comparison with the linear elastic model. So I hope that this video helped you to understand a little bit more plasticity. Plasticity is not an easy topic to study. It's a very complex model to study, and if we want to go to more sophisticated modeling plasticity, we need to have, of course, more knowledge and more understanding. So This is the first video of a series. We're going to study plasticity models which are more sophisticated, and we're going to introduce many more concepts that are interesting and very useful when we do stress analysis in civil engineering, and particularly I'm interested in problems related with solid structure interaction. Thank you very much for watching.